this is example 3a, and 2xy is just 2 times x times y. 3x squared, I wrote it out as 3 times x in case there was an x in the bottom somewhere that could cancel with one of them. You know what I mean? But there's not. It turns out when you're looking for things to cancel here, just this y and this y can cancel. When one's in the top and one's in the bottom, they go away.
Cancel the 2 and the 4?
You could reduce the 2 and the 4 if you'd like. It's kind of like this, everyone. 4 is 2 times 2, right? Say right. Thank you. So one of these 2's could knock out that 2. Got it? Now for multiplying, you just multiply the top and multiply the bottom. So go across the top and tell me what x times 3 times x is. 3x cubed. And on the bottom, z times 2 times z is 2z squared, and you're done. There's nothing else to do. No, those aren't as fun as, ooh, look at B. Let's go right into B. Ready? So 5x is 5 times x. We're just going to leave it like that, 5 times x. X plus 3, if two things are being added like that, they're not factors. They're called terms. So x plus 3 is like its own little entity. If it helps you, put parentheses around it. X plus 3. Now, multiplying. Can this, that I'm circling in green, be factored? I believe it's x plus 3 times x minus 2. Check my work. I think it's right. Can this, in blue, be factored? I think it's x plus 1 times x plus 1. Good? Good? Can this, in purple, be factored? Yes. X squared plus x. Each term has an x in it, so you can undistribute the x. I think it's x times x plus 1. You can check my work by distributing the x. X squared plus x. Okay? And finally, 5x minus 10. There's no x in both of them, but they're both, 5 and 10 are both multiples of 5. So you can undistribute or factor out a 5, leaving x minus 2. That's step 1 in multiplying these massive rational expressions. Break them down into their factors, their components. Just like you do with numbers, break these expressions down into their factors so you can look for things to cancel, because that's the next step over here. I know if you're watching the video you can't see this, but on the board it says, after you factor the numerators and denominators, cancel what you can. So, do we see a match with 5? Anything in the bottom that's just a 5? Yes, those 5's can cancel. Just like we canceled the 2's in the previous problem. Is there a plain old x in the bottom? Just a lonely x? No. Is there an x plus 3 that matches the one in the top? Yes, cancel it. Is there an x minus 2? Top and bottom? Yes, cancel them. Sorry for all the colors. It's going a little crazy here. Is there an x plus 1 in the bottom? Well, there's actually 2, but only cancel one of them. Once everything is canceled, you can see what we have left. Up in the numerator, multiply the top. The 5 is gone. X times, who's left? Another x. So what's that? X squared. Over. The x plus 3 is gone. The x plus 1 is gone. But that x plus 1 is still there. X squared over x plus 1. That's actually your final answer. We reduced that big, ugly multiplication problem and turned it into this. All right? The last step says state any vertical asymptotes and holes. Where would they be? Well, there'd be a lot of them, right? In this original function, there would be holes at -3, -1, and 2. There's no hole at 5. Constants don't create holes in the graph, okay? Just variables. So there would be holes in the graph at -3, -1, and 2. To find their y coordinates, you'd plug each of those numbers into this and see what you get. That's where the holes would be. On the homework and on the test, I'm just going to ask you to get it to this. We're not going to be asking you the vertical asymptotes and the holes for these types of problems. Okay? Just for the ones where you're reducing a fraction. On these multiplication problems, you're not going to be asked to find the vertical asymptotes and the holes. I'm going to eliminate that from the list here. I just realized that.